So this is the premise of the lab we're doing this week. I'm going to demonstrate it here so that you have an idea of what's coming up. And then next day, we're going to give you some simulated data of how to actually complete this lab. But this is the theory behind it. So I'm going to set up a simple circuit here. I have a battery that is set at the default of 9 volts. And when I bring in my voltmeter, hook up the leads to the ends, it makes sense. It reads 9 volts. What I'm going to do now is I'm going to put this in a simple circuit. I'm going to put a resistor down here and attach some wires to it. And current flows kind of like how I'd expect. But then if I use the voltmeter to measure the voltage across this resistor, I only get 8.18 volts. And that seems to defy Kirchhoff's laws because Kirchhoff's loop rule says that the voltage gains and the voltage drops around a loop have to be equal. Basically what it means is you have to use all the energy you get. You can't save it. If you get 9 volts in the battery, you have to use 9 volts in the resistor. And then you get 9 volts in the battery, and you use 9 volts in the resistor, and so on and so on. So this seems kind of peculiar that I'm only getting 8.18 volts across this resistor. If I go up to the battery, I actually get the same thing. So it seems like there's some voltage missing. Or an alternative way to think about it is that it seems like there's some resistance in this circuit that we are not accounting for with this 10 ohm resistor. So what the lab is about is looking at the fact that we assume that batteries are ideal. We assume that they have no resistance. We assume that they do what they say they're going to do when they have 9 volts stamped on the side of them. But the reality is that batteries do have some resistance to them. If I click over here on the right-hand side at battery resistance, I can see that this battery has a resistance of 1 ohm. So this is the lab that we're going to do. What we saw with that FET simulation is that the resistor that's out in the circuit down here, which I'm going to label with a capital R for now, is not the only source of resistance in the circuit. We kind of work into the assumption that batteries are perfect and that wires are perfect and that they don't contribute any resistance to the current flowing through. But the reality is that they do. Even the wires, if we knew what they were made of and how long they were and a cross-sectional area, we could actually determine what the resistance of the wiring would be if we had all that data to account for it. And where we see that happening is that wires have a tendency to heat up. If you've ever held onto some kind of charger or something that's malfunctioning, it feels very, very hot. This is different than like your laptop feeling hot. That's more about the heat generated in running programs and things like that. But if you think about just a wire, we've all had experience of something being a little warmer than it should be. So the lab is about looking at the resistance in the power source itself. So this is my diagram from the FET simulation where I had a battery, which I've drawn like a battery and not using circuit symbols yet on purpose, and one resistor out in the circuit. And what we did is that we measured this potential difference. I stuck my voltmeter around the 2 sides of the battery. But we got a value that was less than the voltage of the battery itself. And that's because inside a battery, we can model it as being the cell itself and a little resistor. This one I'm going to use a lowercase r to signify that it is the internal resistance of the battery. So when a battery says it's 9 volts, it's really talking about this in here. If I could measure somehow this voltage, this would get me the 9 volts. Whereas this got me, I think it was 8.18 volts. We can't actually measure that green one. That would be if I could stick the leads of my voltmeter in through the battery, which I do not recommend doing. It won't actually work and will release the chemicals that are inside. But if we could measure that voltage, we'd get the 9 volts. So we have to take into account this fact. We have to account for the fact that there's really only 8.18 volts being supplied to the circuit itself. And that if I have a larger current running through, if I'd stuck an ammeter here and measure that current, if I increase that current, that's going to change that 8.18 value because there's a current running through the internal resistance of the battery. And I could actually figure that out. I could figure out that the voltage drop here is whatever's missing, that 9 minus 8.18. So the question is, how do I determine, or how do I know how much voltage is actually available to the circuit itself? So we're going to do a little algebra here. So this gets a separate symbol. We have to clarify whether we mean the voltage of the battery, that ideal maximum, or we mean the terminal voltage, aka at the ends of the battery. So if I just draw my battery here, there's the cell inside, there's the little resistor. We talk about this voltage using a symbol epsilon, the Greek letter, which is called the electromotive force, or EMF. This isn't actually a force. This is sort of a holdover from earlier days of studying and quantifying circuits where they talked about it in terms of an electric force or an electric pressure. It's not actually a force. This is still a voltage. Put that there to remind you. So its units is still the volts. And this is this ideal maximum. Whereas the terminal voltage is the voltmeter measurement that I can actually take at the terminals of the battery. And this is what's available to the circuit. So I'm going to use Kirchhoff's loop law to be able to quantify this, to be able to put a formula on this. So when I look at my circuit, if I start at this terminal of the battery, and I flow this way, conventional current, positive to negative, I have two voltage drops. I have one voltage drop as I'm going across the resistor that's out in the circuit, and I have one voltage drop when I go across the internal resistance. It's really just the same thing as a series circuit with two resistors. It's just that one of those resistors happens to be inside the battery, so I can't measure it in the same way. So Kirchhoff's law says, however much I gain in the battery, I use in the circuit, or I use in the resistors. So if I get 9 volts from the battery, some of it is used in the external resistance and some of it is used in the internal resistance, but I have to use it all up. Gain 9, use 9. Gain 9, use 9. So if I think about this in terms of a formula then, that voltage gain, the EMF, has to be equal to the sum of those other two. The terminal voltage, or the voltage available to the circuit, plus the voltage drop inside the battery itself. Then I'm going to use Ohm's law to kind of simplify this a bit. The voltage drop in the battery is just the current times the resistance in the battery, which is that little r. And then if I bring that over to the other side, my terminal voltage is equal to that ideal EMF minus the voltage drop in the battery. So this is the premise of the lab that we're going to do next day. We are going to have different amounts of current running through our simple circuit. It's going to look just like the one I built on FET. And if I put different currents through this circuit, that's going to change the terminal voltage. It's going to change the amount of voltage drop in the circuit itself because this second term will change.